In the name of God, the most merciful, most kind, peace be upon you all. This is a new video, and our subject today is talking about the permutation matrix. And from Pivoting for LU Factorization by Matthew W. Reed, I quote this explanation. First, a permutation matrix is an identity matrix with interchanged rows. We have spoken about elementary matrices before, and we have included that we have mainly three identity matrix types. The first type is created by interchanging rows. Second type is by multiplication any row of a matrix by a scalar. And the third type was multiplying rows and adding to another rows. This is the three types. We are going to focus on the first type. This permutation matrix, if it is multiplied from the left side of a matrix, it makes a swap between rows. Left multiplication by permutation matrix will result in a swapping of rows, while right multiplication will swap columns. In the next slide, we are going to focus on the 2 by 2 matrices. The identity matrix, as we know, for 2 by 2 is diagonal equal to 1 and 0 elsewhere. If we have a matrix A, B, C, D, and we multiply it by the identity matrix, there will be no interchange between rows because it is the normal form of the identity matrix. We multiply 1 by A is A, and 0 by C is 0. And the second row will create C in the second row first column, and the D in the second row second column. In that case, when we multiply I by A, it will result as a matrix. We will not have any change in matrix A. But if we want to change the rows of matrix A, for instance, making swap from row 1 to row 2, we need to use what is called permutation matrix, which is type E1 from the elementary matrices. We can see that we make a swap of the identity matrix. Instead of 1, 0, 0, 1, we have swap the first row to become second and the second row to become first. What happens if we have 0, 1 as a first row? When we are going to multiply 0, 1 by AC, we get C here, and we have D here. While the row that's being multiplied by 1, 0 will be changed. It will become A here in the second row first column, and we have B here in the second row second column. So in this 2 by 2 matrix, to change the arrangement of the row 1 to row 2 and vice versa, use permutation matrix denoted by B. And that permutation matrix is to be multiplied by A from the left side. As we can see, 0, 1, 1, 0. We move to the next slide. The second case, if you want to change the arrangement of columns of matrix A, we are going to make the swap in the permutation matrix, but we will multiply matrix A by the permutation matrix to the right side. So we have A by the permutation matrix will lead to swap of column, as we are going to see. We have matrix, suppose we have A, B, C, D, and we want the BD to be the left side and the AC will be the right side. What can we do? If we have the identity matrix, then we will have a diagonal here 1, 1, 0, 0. we are going to change the column. The column as the first case was 1 0 0 1. We'll make swap of column. We make the 0 1 as the first column, while the 1 0 as the second column. When we multiply AB by 0 1, we have B here, and we have A here, and we have D as A 2 1, and we have C by 1 plus D by 0, we get C as A 2 2. How many numbers of operations we can do? 2 factorial 2 by 1. B12 is the normal way where the identity matrix is arranged 1 0 0 1, while B21 is the situation of the permutation when we replace the second row to become in lieu of the first row. We'll check the next slide. B12 is the normal situation 1 0 0 1. When we multiply by A, B, C, D, there is no change. While if we change the second row becomes the first row and the first row becomes second, we call it B21. When we are going to multiply by the ABCD matrix, we will find that the AB, instead of being in the first row, will become the second, and the CD will move up. In the next slide, we'll start to discuss the permutation matrix for 3 by 3 matrix. This is the normal identity matrix. We call it B123. What are the forms? What are the possible patterns that permutation 3 by 3 can have? We have 6 patterns. The first pattern is the normal one, 1 2 3 of the identity matrix. The first row is 1 0 0, second row is 0 1 0, and the third row is 0 0 1. We have a diagonal equals to 1. This is a diagram. We have 1 2 3. What is the possible of the other pattern? And still we have 1 here. The only possible that we, instead of 2, it will become 3, and instead of 3, it will become 2. This is the second pattern. For the third pattern, we have 2 at the top. What are the other remaining numbering? We have 1 and 3. So we have 2 1 3. And the next possibility for that pattern is to have 2 3 1. And the last pattern, if 3 is at the top, then we have 3 1 2, or there is a possibility of 3 2 1. Okay, for B1 2 3, we have the first row, second row, third row. But for B2 3, we have row 1, row 3, row 2 by order. And 2 1 3, we put R2 as first, then followed by R1 in the second row, followed by the R3 in the third row. Then we have 2 3 1, second row, third row, then first row, and the last two figures R3 R2, R3 R1 R2, and the last pattern is 3 2 1, R3 R2 R1. If we count them, we have 1 2 3 4 5 6 possibilities of arrangement. B213 is the second row, followed by the first row, followed by the third row. Second row was here. It moves up to become the first row. So we have 1 0 0 1 0 here, followed by the first row that was 1 0 0, and the last row is still the same. So here is the replacement. Instead of 1 2, it becomes 2 1. This third matrix, we have B3 1 2. Instead of the first row, the third row will come up, which was 0 0 1, followed by the first row, which was 1 0 0, and the second row go down from the second position to the third position, 0 1 0. B3 2 1. The third row 0 0 1 will become the first row, followed by the second row. There is no change here, and the first row will become the last row. The first row was 1 0 0. It will become the third row. B1 3 2. The first row is the same, no change between the identity matrix, and the third row 0 0 1 will move here, followed by the second row, which is 0 1 0. First row 1 0 0, it becomes in the third position. B1 3 2, 1 0 0 is here, followed by the 0 0 1, followed by 0 1 0. And B2 3 1, second row followed by the third row, followed by the first row. Second row 0 1 0, third row is 0 0 1, and the first row is 1 0 0. The next slide. We'll start to review B2 1 3. Second row, first row, third row. Second row 0 1 0, 1 0 0, 0 0 1. What happened? Suppose you have matrix 2 3 4, 1 9 3, 5 6 7. The first row here, it is replaced by the second row, so it will move to the second row. And 193, the second row, will become in the position of the first row, while the third row is the same, 5 6 7. In the next slide, we will review the B312 permutation 312. The first row is 0 0 1, second row 1 0 0, and 0 1 0 is the last row. Again, we are going to multiply by our matrix 2 3 4, 1 9 3, 5 6 7. We check this pattern. This is A, and this is B, the final. When we multiply from the left, the first row would become here as a second row, as the second row will move down, and the third row will move up. The third row 5 6 7 will move up, and the second row will move down 1 9 3, and 5 6 7 will move up. 3 3 1 and 2. We move to the next slide. We take the position of permutation B3 2 1. Instead of 1 2 3, the normal arrangement, which was 0 0 1 0 1 0 1 0 0, 1 0 0 would become up, and 0 1 0 is the same, and 0 0 1 will go down. Again, R1 will move to the third position, R2 will be the same position, and R3 will move to the first row. So R1, 2, 3, 4 will become the last position, third row, and the second row is still the same, 1 9 3, 1 9 3, and the third row will move to become the first row in matrix B, and here is again the arrangement 3 2 1. B132. Instead of 1 2 3 by arrangement, we have the first row still the same, while the second row will move down and the third row will become as a second row. R1 same, R2 would be changed to R3, and R3 will become in the second row. The arrangement 1 0 0 0 0 1 0 1 0, and here is 2 3 4 1 9 3 5 6 7. 2 3 4 in the first row, because we have 1 0 0, it is a normal position, and 0 0 1 will take 5 6 7 to become here, and 0 0 1, which is related to the third row, will move the third row up 5 6 7. Always 1 0 0 will maintain the row. For the last permutation, I believe, B231, B231. The 1 2 3, we have second row followed by the third row followed by the first row. So second row 0 1 0, third row is 0 0 1, and the first row is 1 0 0. We'll multiply by 2 3 4 1 9 3 5 6 7. This will bring the second row up, and this is related to the third row, so it brings the third row here. And last, the first. In the last slide, we are going to talk about one of the properties that the permutation matrix multiplication by its transpose will lead us to an identity matrix. For instance, if we have permutation B312, arranged as 0 0 1, 1 0 0, and 0 1 0, when we multiply by its transpose, the transpose will take the columns turned into rows. So first row 0 1 0, second row is 0 0 1, and the third row is 0 1 0. When we multiply both, we get this. Will require that the last row will become as the first row, so it will become 1 0 0 here. The result 1 0 0 will require the first row of matrix A will go down, so it will become 0 1 0, and 0 1 0 will bring the second row of this matrix down. It will become 0 0 1. Due to this property, if we multiply B by B transpose equal to I, it means that this transpose of this permutation matrix is the inverse of the permutation matrix. We'll come to the end. Thanks a lot. I hope this video was useful. God bless you all. Take care and goodbye. This row would be brought down to 3 4.